Hello everyone, I'm Xuejiang from the Technical University of Munich. Today I'm going to present our work on comprehensive analysis of privacy leakage in vertical federated learning during prediction. This is joint work with Xuebing Zhou from Huawei Munich Research Center and Jens Grossklacks from the Technical University of Munich. Federated learning is an emergent distributed learning mechanism which allows multiple organizations to jointly train AI models without revealing their private data. According to the partition strategies of local data, existing FL frameworks can be further categorized into the horizontal setting and vertical setting. In the horizontal setting, each party holds data from different users, while these data share an overlapped set of features. For instance, in a healthcare application, a model for predicting cancer risks is jointly trained by multiple hospitals using the medical records of different patients. In contrast, the vertical setting assumes that each party holds different features of an intersecting set of users. Moreover, only one of the parties has the real labels. For instance, in a smart finance scenario, a bank wants to train a model to evaluate customers' credit scores. Besides using its own features such as age and income, it also collaborates with an e-commerce company and uses additional features such as purchasing history to improve the model's accuracy. Since it is common for companies to collect different user features for their services, VFL systems attracted increasing attention in recent years. Here we present a common two-party VFL system, which includes an active party who has part of the features and real labels, and a passive party who only provides additional features. Moreover, several existing VFL systems also adopt a trusted coordinator to manage the communication between the local parties and to defend against the privacy leakage. During prediction, each party inputs the features of new samples to the trained models and computes the intermediate results. The coordinator then privately aggregates these results, computes the confidence scores via an output activation function, and returns them to the active party. Although the trusted coordinator effectively prevents the direct data sharing between local parties, a recent work by Luo et al. Shows that during prediction, the active party can still use the confidence scores to reconstruct passive party features and cause privacy leakage. In their paper, the authors started with a simple setting, where two parties jointly train a logistic regression model with k-classes. They proposed an equation-solving attack which mathematically calculates the passive party features by solving the following linear equation system. They show that when the number of unknown features dpass is less than the number of classes k, the equation system has a unique solution and the feature values can be fully reconstructed. However, the ESA attack only works for linear models and cannot be applied to complex neural networks. Therefore, the authors further proposed a generative regression network attack, which uses an attack model to learn the feature correlations between both parties and to generate the passive party features. Nevertheless, the attack requires collecting a large number of predictions to train the attack model. Finally, both attacks only considered the white box setting, which assumes the attacker can access the passive party model. This may not always be achievable in real-life scenarios. Motivated by these observations and limitations, we propose and illustrate the threat posed by a gradient-based inversion attack. The attack can be generically applied to different machine learning models and does not need to train an attack model in advance. Moreover, besides the white box setting, we give the first attempt to explore the attack under the black box setting. Next, we will introduce this attack in detail. We start with the white box attack. Similar to the previous work, we assume the attacker, namely the active party, has full knowledge of the entire model parameters. Also, for each new sample, he knows his own input features as well as the real confidence scores. The goal of the attacker is to use this information to estimate the passive party features. Our attack is conducted in an iterative fashion. To begin with, the attacker randomly initializes the passive party features. Then, both part of the features are fed to the trained model to compute the estimated confidence scores. The distance between the real and estimated confidence scores is calculated and used to update the passive party features. This process is repeated for several rounds until the estimated confidence scores are close enough to the real values. Here, we use two metrics, namely the mean squared error and the KL divergence, to measure the distance. Next, we explore the potential privacy leakage under the black box setting. Here, the attacker only knows his model and cannot access the passive party model. We further slightly relax the setting by assuming that the attacker is aware of a small set of auxiliary data. This can be obtained by, for instance, colluding with a few users whose data are saved in both parties. The black box attack can then be conducted in two steps. First, the attacker uses the auxiliary data to train a shadow model to mimic the performance of the passive party model. Then, he can use the shadow model to repeat the white box attack and to recover the passive party features. For training the shadow model, the attacker first initializes a random passive party model. Then, the auxiliary data are iteratively input into the model, and the distance between the real and estimated confidence scores will be used to update the model parameters. Finally, we wonder how much auxiliary data is needed to build a good shadow model. Given the number of model parameters and classes, we derive an approximated threshold tau as the minimum auxiliary data for achieving similar attack performance as in the white box setting. Note that the attack can still be performed with less auxiliary data, but this may lead to a worse attack performance. We conduct our attack on 4 open source datasets and compare the attack results against the logistic regression models and multilayer neural networks. We respectively use the attacks proposed by Luo et al. As the baselines. We adopt two metrics to evaluate the attack performance. For the attack error, we use the averaged mean squared error to measure the difference between the real and reconstructed features. For the attack accuracy, we train an evaluation classifier and investigate whether the reconstructed features can provide the same prediction results as real features. We first report the attack performance under the white box setting against both types of models. It can be seen that we can achieve a zero attack error when the number of passive party features is small, meaning that the feature values are fully recovered. Although the attack performance decreases with the increase of unknown features, our attack shows a significant improvement compared to the baseline algorithms. We further conduct black box attacks against both types of models using different amounts of auxiliary data. It can be seen that the increase of auxiliary data can in general contribute to a lower attack error, and the attack error is similar to the one under the white box setting when the amount of auxiliary data approaches the threshold. Here, for both models, we can already achieve comparable performance with only less than 100 records. The results show that even without knowing the passive party models, the attacker can still use limited auxiliary data to build the shadow model and to apply the reconstruction attack. We further investigate whether the prior knowledge of the model structure is essential for building the shadow models. To this end, we use the two-layer neural network as the real passive party model and compare the attack error of using shadow models with different structures. It can be seen that building the shadow model with the original structure leads to the lowest attack error. Although altering the model structure may increase the attack error, we can still achieve a satisfactory attack performance when the shadow model does not differ too much from the real model. The results indicate that it is still possible to conduct the attack even without knowing the exact structure of the passive party model. Finally, we analyze the performance of different defense techniques, which are either applied during training or during prediction. For the defenses during training, we investigate whether private set intersection, the commonly used sample alignment technique, can help prevent privacy leakage. Moreover, we also analyze the capability of differentially private training against the attack. Here, epsilon is the privacy budget. The smaller epsilon, the higher the privacy protection. For the defenses during prediction, we process the original confidence scores by rounding the values to limited decimal places or adding random noise with different noise scales. We also investigate a purification defense, which uses a pre-trained purifier to perturb the real confidence scores. The processed scores will be decoupled with the input features, but can still provide a good label prediction accuracy. Here, we compare the performance of purifiers respectively trained on real data or randomly sampled data. The two figures report the privacy utility analysis of different defense techniques under the white box setting. The red star represents the area of the ideal privacy utility trade-off. From the results, it can be seen that PSA cannot prevent reconstruction attacks. While training models with DP can reduce the attack accuracy when epsilon is small, it also results in much lower model utility. On the other hand, processing the confidence scores can better enhance privacy protection. For instance, rounding the confidence scores to integers can effectively prevent the attack without affecting the model accuracy. Added noise with a noise scale larger than 0.1 can also defend against the attack, but too much noise may cause a significant utility loss. Finally, perturbing the confidence scores with purifiers trained with both real data and randomly sampled data can in general achieve a satisfactory privacy utility balance. In conclusion, in this paper, we propose and discuss the threat posed by the gradient-based inversion attack, a generic framework that performs feature reconstruction attacks on VFO systems during prediction. The attack can be flexibly applied to different machine learning models and outperforms the prior work. We further explore the attack under the black box setting and show that attackers with limited prior knowledge can still infer the passive party features even without knowing the target model's real weights or the model structures. Finally, we analyze the privacy utility trade-off of several defense techniques. We show that the proposed attack cannot be simply prevented by using a trusted coordinator. Instead, processing the confidence scores with quantization and randomization approaches can be useful for strengthening privacy protection while having only negligible effect on model utility. Thank you for listening.